Well, here we are at lecture 2C, and what we're going to look at today is the heats involved in phase changes. We may be doing more than one phase change, in which case we have to account for the amount of heat needed to change the temperature as well. And so we're going to look at one other process. We looked at the heat of vaporization in the previous lecture, and here we're going to look at the process of fusion. Fusion is a process of coming together. Normally when you hear fusion, you think of the idea of nuclear fusion. That's not what we're doing. We're not fusing nuclei here, but it's still the same process. We're still taking things and putting them together. Nuclear fusion involves putting nuclei together and changing the actual atom there. Here we're just taking molecules and putting them together, generally with intermolecular forces. So that's what we do when we turn a liquid into a solid, is we are fusing those molecules together into a single entity. Now, when we take a solid and we want to add heat to it, we can do one of two things, but we can't do both. So we can either change the temperature, so we can raise the temperature of that solid, or we can change its phase. The key here, though, like I mentioned, is that you cannot do both at the same time. And so if you're between phase change temperatures, then you're going to be changing the temperature. Once you reach a phase change temperature, such as a melting point or a boiling point, then you're going to be adding heat in order to change the phase. When you're changing the phase, the temperature doesn't change. Now, we hear the term heat of fusion, putting things together. So that's the amount of heat that will be released when a liquid turns into a solid. It's also the amount of heat that needs to be added to a solid to change it into a liquid. So you can also think of it as a heat of melting if you'd like to do that. So here's kind of what I was just mentioning. So if we know this is for a sample of water, and we've got a sample of water at minus 10 Celsius, and we want to bring it up to like 35 Celsius. And so water at minus 10 Celsius is well below the melting point of zero. And so as we add heat to our ice sample, we have to raise the temperature of that water until we get to here. Okay, so notice that we have to add heat. And so once we get to this point at 0 Celsius, well, now we've reached the phase change temperature, 0 Celsius. And at that point, the water is going to stop changing temperature. So it's going to stop using the heat to raise its temperature, and it's going to start using its heat to break those intermolecular forces. It's going to turn solid into liquid. But during that time, the water does not change its temperature. At this point here, all of our solid has been turned into a liquid, and now the heat that's being added can be used to change the temperature once again, and so the temperature begins to rise. Okay, there's never any exception to this. When you add heat to a material, you can either change its temperature or you can change its phase, but you can't do both. Generally, the heat of fusion for a substance is quite a bit less than the heat of vaporization. So if we look at water here, the heat of fusion is sitting down here around 6 something, and the heat of vaporization is up around 40.7. Rubbing alcohol, isopropyl alcohol, is also down around 6, and its heat of vaporization is up around 40. Acetone, right around 6, heat of vaporization just under 30. Diethyl ether, a little more at about 7, and its heat of vaporization is up over 25. So significant differences, and you have to take into account of what's going on. When you're melting something, you're not completely breaking those intermolecular forces. All you're doing is changing them, making them more mobile. When something is in a liquid phase, those intermolecular forces are still present, and that's why it's in a liquid phase. However, once you want to change it to a vapor, into a gas, you have to completely break all intermolecular forces and separate those molecules so that they don't recombine. So let's look at a heating curve and what it might look like going through some different phases, or we'll look at one here in just a moment. Now, when we use these heating curves, we can actually find the melting point and we can find the boiling point if we heat something up to that extent. And we can do that for an unknown substance. So what we do is we plot the amount of heat added versus temperature, or you can actually plot it as time versus temperature. If you know how much heat is going in, then you can extract out how much heat is going in there. But let's take a look at a curve here on the next slide. And what we're going to do is we're going to take 1 mole of water. It's going to be starting as ice at a very cold temperature at minus 25 degrees Celsius. And we're eventually going to turn it into steam at 125 Celsius. So we're going to take a sample of water that's 25 degrees below the freezing point and turn it into water gas that's 25 degrees above the boiling point. Now we have a couple of equations that we want to take a look at. So these two equations are all you need to do these calculations. Anytime you're within a phase, and so you're changing the temperature of the water, we use the equation that's heat is equal to C times M times delta T. C is the specific heat for that substance in that phase, and usually liquid phases, solid phases, gas phases for a single substance have a different value for C, so you want to make sure that you're using the right one. Your M is just the mass. As long as your sample is in an enclosed system, your mass remains the same. And then the delta T is just how much are you changing the temperature by to get from one phase to another or within that phase. Okay, now something to keep in mind with this calculation is your C's are usually in joules per Kelvin mole. So your heats come out of this equation in joules. If we come down here to this next equation, so this is the equation you use when you reach a phase change boundary. So once you reach the temperature of a phase change, so like 0 or 100 for water, we're going to take the delta H, and they just have X there because the X is either vaporization or fusion. Which heat change, which enthalpy change are you doing? What's the enthalpy of that phase change? So X just represents the different enthalpies of phase changes. So either vaporization or fusion. Times N, where N is the number of moles. Okay, this is another stumbling point. So for your heat involved at a phase change, you need the number of moles. And when you're doing your within a phase, the equation uses the mass. So you want to make sure that you don't mix those two up. So the other thing to keep in mind is that at a phase change, your delta H, either a vaporization or a fusion, is usually in kilojoules per mole. And so this calculation is going to come out in kilojoules. So you have you're going to have a joule unit here and a kilojoule unit here. And so you've got to make sure that you change one to the other so that you can add those values together with the same units. All right, let's see how this works. And so here we've got our water ice sample initially at minus 25 Celsius. We haven't added any heat. So we're going to add heat until it reaches the melting point up to 0. Okay, and if we do that calculation to go MC delta T, we would get 941 joules that we put in there. And since it's 1 mole, that would be 0.941 kilojoules for those 18 grams, and that would be per 1 mole. Okay, so that really didn't take all that much energy in comparison to heat that ice up a little bit. Now, once we reach 0, we have to change the phase. So we have to keep the temperature the same. The temperature, I shouldn't say we keep it. The temperature isn't going to change. All the heat that we add is going to go into breaking those bonds that we see in the ice, all of these intermolecular forces that are present in the solid. Notice that water molecules are still all in contact with each other, so we haven't broken them completely, but now the water is more mobile. So we're going to use the equation where we use the delta H of fusion times that 1 mole, and so that's going to give us 6.02 kilojoules per that 1 mole, so we have 6.02 kilojoules. And now we get this point here, and all of our ice has been turned into liquid. Now we have to heat this liquid all the way up to 100 degrees Celsius. So we have to go from 0 to 100. And so again, we use MC delta T. Our delta T here is going to be 100 because we're going from 0 to 100. The number of grams, or our mass, is going to be 18 grams because we have 1 mole. So when we do that calculation with our value of C for liquid water, we're going to get right around 7,520 joules. And since we have 1 mole and we convert it into kilojoules, we're going to get 7.52 kilojoules per mole. So that's how much we had for phase 3. Now, once we reach 100 degrees Celsius, we're now at the boiling point of water. And we have to change all of that water into steam. So now we have to completely break all of those intermolecular forces. All of those hydrogen bonds between water molecules need to be broken. And we can see how much energy it takes in order to break those bonds. It's a significant amount of energy. So again, we're going to use delta H X, so delta H vaporization times the 1 mole, and we're going to get 40.7 kilojoules in order to go into that. And now we're not done, because now once we finish doing that, we've got all of our water at 100 degrees Celsius, and now we need to move it into steam at 125. So we need to add a little bit more heat. We need to use the specific heat for water in the gas phase. The delta T here is going to be 25 because we're going from 100 to 25, and our mass is still 18. So if we take all of these numbers for kilojoules and add them up, that would be the total amount of heat that we had to add to get there. So hopefully that helped clear some things up. We will see some calculations like that on practice problems, possibly on homeworks. So if you have any questions on that, please make sure you contact me.